Hey, P Statistics, welcome to section 9.2, where we're going to look at actually performing a significance test for a population proportion. That's going to be kind of similar to last chapter, where in 9.2 we're going to do proportions, and then 9.3 we're going to do means. By the end of this section, you should be able to state and check the random 10% and large counts conditions for performing a significance test about a population proportion. Good news is that's mostly the same. There's got a lot of regurgitation of things. Little differences, though, so make sure you're paying attention. I'll call those out. Calculate the standardized test statistic and p-value for a test about a population proportion. We're going to actually get to where we can do that, and perform a significance test about a population proportions. We're going to get to by the end of this section, you should be able to do a full state plan, do, conclude. We'll do that in the next video. All right, so conditions. We're doing this stuff based on sampling distributions, and so our same conditions are back. We've got our random condition, that the data come from a random sample from the population of interest. We don't want a biased sample to draw our conclusions from. We want a nice, random, representative, unbiased sample. Then there's the independence, the 10% condition. So when we're sampling without replacement, we want to make sure our sample is less than 10% of the population. Great news, those are the exact same as they have been for the last couple of units. The slightly new one here is the large counts condition. So originally back in confidence intervals, sampling distributions, we checked n times p and n times 1 minus p, and it was great, and they told us what p was. Well, then in last chapter, we didn't have p. We were trying to estimate p, and so we used p hat instead. Well, now we're going to switch to a third thing. It's kind of back to the original. We're going to use p naught. So whatever our assumed proportion is, we'll start out these significance tests with a null hypothesis of p equals a number, and we call that p naught, our null hypothesis. Because basically we calculate our math in this chapter based on the assumption that that null hypothesis is true. Assuming the null hypothesis is true, what's the probability of this? And so we imagine a sampling distribution from that null hypothesis. And so we check n times basically p and n times 1 minus p. It'll be written, in the null hypothesis. But that needs to be at least 10, and that satisfies our large counts condition, so we can actually use a normal distribution. And some z-scores are going to get involved here, and so we can do some normal calculations. So because we assume the null hypothesis, I think this is what I just said, the null hypothesis is true when performing a significance test, we use the parameter value specified by the null hypothesis, in this case denoted p naught, when checking the large counts condition. So for a test, use the null value p naught, not the sample proportion p hat, to check the large counts condition. That is the expected counts of success instead of failures, instead of the observed, like we did for confidence intervals. So that's the one big difference in those conditions. All right, so an example problem here. According to the U.S. Census Bureau, the proportion of students in high school who have a part-time job is 0.25. An administrator at a local high school suspects that the proportion of students at her school who have a part-time job is less than the national figure. She would like to carry out a test at a 5% significance level. So note that a lot of times this is based on comparing one group to another. And so we know it for one. We want to know if this group is the same. Or it might be comparing to the past. In the past, it's been this number. Is it different? So that's where a lot of these types of problems will come from. So we have to have some assumed null hypothesis. Somebody's got this claim, and then we're trying to test this other claim. So I don't know, I guess they're both claims, but the null hypothesis is this kind of the status quo, same 0.25, and then we're finding evidence that it's less than 0.25 at a 5% significance level. So P is the true proportion of students in the school this school in particular, that have a part-time job. The administrator selects a random sample of 200 students from the school and finds that 39 of them have part-time jobs. Check the conditions for performing a significance test are met. And so we're going to want to go through those same exact three. We're going to check the random condition. And so in this case, they did select a random sample of 200. We're good. The 10% condition. We want to make sure that 200 is less than 10% of the school. Well, they did say it's a large high school, so hopefully they have at least 2,000 students. So we'll assume that. I don't think they say that yet. We'll assume that. And then the large counts, we're going to go up to this P right here. There's a lot of things you might think to use, right? You might think to use this P hat, this 39 out of 200. That would be P hat. We don't want to use that. We want to use this null hypothesis, 0.25. So 0.25 n times that, 200 times 0.25 is 50, which is at least 10, and 200 times 1 minus 0.25 is 150. Both of those are at least 10. All right, so performing a significance test, we're going to go back to this null hypothesis here. A basketball player claims to be an 80% free throw shooter. You think that player is exaggerating. So the null hypothesis, this is a mistake. It should be P equals 0.8. And the alternative is that P is less than 0.8. Sorry about that. If the null hypothesis is true, if P did equal 0.8, if this person really was an 80% free throw shooter, what values of P hat would we expect in a random sample of 50 shots? All right, so we actually can think about the sampling distribution. This is going right back to chapter 7. Like I said, that kind of forms the foundation for both confidence intervals and significance tests. So our null hypothesis is that P equals 0.8. And so if that was true, we would expect we can think of kind of go over shape, center, and spread. The shape would be approximately normal as long as the large counts can do it. So because the large counts condition is met, the shape of P hat will be approximately normal, the P hats we would expect from that. If that null hypothesis is true, the center will be at 0.8 if it's unbiased, so it'll match that 80% that we're assuming is true. We do the problem assuming it's true, and then at the end decide if that assumption was correct. And then the spread, so we use that square because we can deal with the independence, the less than 10%. So we can use that standard deviation formula, square root of P, and then times 1 minus P over N. But notice again, we're using P naught. We're using kind of our best thing we can before with confidence intervals, it was P hat. Here we can actually use our null hypothesis. We're assuming P is 0.8 right now, and so we plug in 0.8, sample size of 50, and so that's the spread. And so we can actually get our shape, center, and spread, and there's a picture of what it looks like. And so we have it centered at that 0.8. We got the appropriate standard deviation, the normal distribution. There's our sampling distribution that we would expect if the null hypothesis is true. Well, this person made in their sample 32 out of 50, or 0.64, which is way down here. And if you find the probability of getting something that or lower, and this is why we actually say you always got to go inequality because it's a normal curve we're going to use. It's tiny, and so we want to figure out how to calculate that exactly. What I want you to focus on is actually, we could do this normal CDF in our calculator, but I want you to turn this into a z-score. This is something that they're going to look for. We're going to calculate a z-score for that value. And so we take that P hat and we plug it in, and so we do, and this is going to be our formula that we're going to use for our significance test for proportions. So you use your sample proportion, find how far it is from the population proportion, or the assumed population proportion, in this case 0.8. So our sample below here is 0.64. How far is that below 0.8? And we want to do it in terms of standard deviations. Figure out how many standard deviations from the mean we are, in this case below the mean. And so we have our standard deviation formula we calculated on the other slide here. So in this case it's 0.8 times 1 minus 0.8 over n. That would be that number. And so apparently that's 2.83 standard deviations below the mean, which is pretty far, and we'll calculate the probability in a second. That'll be our p-value. But you need to know what this number is. You could do it in your calculator without finding the z-score, but this is actually known as the standardized test statistic. So there's a few terms in here. The test statistic is just the 0.8, or sorry, not the 0.8, the 0.64. All right, it's the actual 34 out of 50. Was that what it was? So 32 out of 50, right? Yeah, 32 out of 50. So that's our test statistic. Our standardized test statistic actually turns it into a z-score, and so that's what we're going to want to be able to. You're going to want to be able to identify that, and then you can calculate the probability based on that. But this standardized test statistic is going to exist in all of our significance tests. So a standardized test statistic. That's a mouthful. A standardized test statistic measures how far a sample statistic is from what we would expect if the null hypothesis were true in a standard deviation. That is, our standardized test statistic is statistic minus parameter divided by the standard deviation of the statistic. So it's basically a z-score for your statistic, a z-score for your x bar or your p hat. In this case, we're focused on p hat, but we'll come back and do that with x bars. This is actually on your formula sheet, though they have changed it. It's really the standard error of the statistic that they refer to. Well, I guess this is never mind. This one is the same. Standard error, we're using the sample. This one we're using hypothesis, so we are good on that. Sorry. So you can take that same exact graph we saw in raw proportions. We can convert this into z-scores. You have your standardized normal curve versus the actual normal curve. And so we can find the p-value, the probability, which is this tiny little shaded region here, using Table A or technology. Of course, I'll recommend technology. They do Table A. You could look up negative 2.83 in your table, your z table, and find that. But more likely, you're going to want to do this, normal CDF. And then you have lower bound, upper bound. So we're going from negative infinity, I usually use negative 1e99, up to 2.83, negative 2.83. Oops, yep, that should have a negative 2.83 in there, not a positive 2.83, with a mean 0 and standard deviation 1. And so that's in our standard normal curve, and you get 0.0023. Technically, you'll get that same probability if you use the normal CDF up to 0.64 with that mean and standard deviation. But on these types of problems, they want you to show that standardized test statistic. So I'll want you to do that as well to convert it into a z-score. In the preceding example, an administrator at the local high school decided to perform a test at the 5% significance level. The proportion is 0.25. This is the proportion that work versus less than 0.25, where P was the true proportion of all students at the school who have a part-time job. The administrator selects a random sample of 200 students from the school and finds that 39 of them have a part-time job. So we already confirmed that the conditions for performing the significance test were met. Now we're going to explain why the sample results give some evidence for the alternative hypothesis, calculate the standardized test statistic and p-value, and what conclusion can we make based on this. So starting with explain why the sample results gives some evidence for the alternative hypothesis. Well, 39 out of 200 is less than 25%. So there's some evidence. That's pretty much all we have to say. The sample proportion of students at this school with a part-time job is 39 over 200, which is 0.195, which is less than the national proportion of 25%. So as suggested by the null hypothesis. So yeah, we are suggesting that one. However, we can't conclude it just because it's lower. So we're going to figure out a p-value for that. So calculate the standardized statistic and the p-value. So we take our sample proportion minus p naught, and so we figure out that we're below it. But how many standard deviations are we below it? And so we're using the standard deviation. We plug in that 0.25 and the 0.75 over 200 square root, and that's going to give us a z-score. Apparently, we're 1.8 standard deviations below the mean. And so if we draw a graph of that, we can find that. Draw a little z curve here, a standardized normal curve, find the area below that since this was a one-tail less than test, and find that corresponding p-value. So you could use the table, or you could use what most of you are probably going to want to use is the normal CDF, but you can either way draw it based on this curve. So in this case, the lower should be not that. We are going to go negative infinity, negative 1e99, sorry, I made a typo there, up to, and then this should be, what was our z-score? Yeah, they're copying and pasting some terrible numbers here. So up to 0.035, nope, that's not it. Sorry, my z-score, negative 1.8. So negative 1.8 was what that one should be. I think they did 2's instead of a negatives. That's what it was. So it should be, they went negative 1,000 up to negative 1.8, but it should be, I do negative 1e99. Up to negative 1.8, there's that number. With that mean 0 standard deviation 1 since it's a standardized normal curve, and you get a 3.59 value for our p-value. There's a 0.3059. And so what conclusion would we make? So because that p-value of 0.0359 is small, less than our significance level, we reject the null hypothesis. We say, yeah, that's really unlikely. If there really were 25% of students at this school, it's really unlikely that we would get a sample that low. So we reject that claim and accept the alternative. So we have convincing evidence that the true proportion of students at this large high school who have a part-time job is less than 0.25.